Second session of this workshop, and so without further ado, I will introduce the keynote of this session, and please welcome Confan to this to the stand. Thank you very much.
Thank you very much. I have the pleasure to start this session. So they asked me to wait a little bit. So they're going to start the presentation. So just to say that in this second session, we will be 5 speakers, including myself. So I have the pleasure to start this session, and I will try to explain a little bit what, from my perspective, is important when dealing with usage of data and sharing of data. And hopefully I will succeed to introduce the main topics that will be addressed by the following speakers. So use and sharing of data for planning and decision making. So that's the title of this session. Am I going to talk about robots? I actually didn't know what FIRA before having been invited here. I'm not working in the field of robotics, so the answer to this question is no. I'm not going to talk about robots. And then you may ask, why? Because we are in a robotic show here. Well, first because I'm not a robot expert. That being said, robots means action. So you want to do something with the robots. I believe that there are in the audience here many people that are more competent than me about talking robots. So I would just summarize. Maybe it's partly true, but robots for me is more when you know what you're doing or you know what you want to do, and then you ask the robots to do it. I'm not saying that it's an easy task, for sure, but it's, let's say, the final step, I would say. So, plan and decide first, because in order to be able to use the robots or to know what you want to ask to the robots, you first need to plan and decide first, okay? So this is the subtitle of this session. So how? And that comes to the title of the session. Get and use data first to plan and decide, then run robots. Okay, so not being a robot expert, I definitely choose let's say, an orientation for my presentation. And I will try to tell you my feeling or my perception on how we can use data and how we can share data in a more efficient way. So in this session, as I said, we are 5 speakers, including myself. And if you look at the keywords that I took the liberty to pick up in the titles, what you see is interoperability, better understanding, real-time, harnessing data, intelligent data sets, and so on. So definitely it's all about data. What kind of data are we talking about? There's a lot of data from the agricultural point of view, okay? And for those who don't know this very good book from FAO, Farm Data Management, Sharing, and services for agricultural development. There's actually a lot of data. And we could talk about farm-level data, could be field information, production information. So I think that's a lot of the topic addressed in what FIRA is how to get farm-level data. And this is where I will focus my talk, how we could get real-time data on field information, probably for production enhancement, but to try to improve any kind of agricultural process. But of course, there's a lot of data that I'm not going to talk about. Agricultural laws, regulation, financial instrument, data sets for farming, agriculture. By data set, we know that usually with the AI, let's say, buzzword, we map data set to AI processing, okay? But data set is going far beyond AI. Data set has its name indicate a set of data. So there's a lot of data set for agriculture coming from various organizations for land use, productivity, value chain, infrastructures, markets, statistics about this for farmers to know or to start their business or to know a little bit what's going on the market, okay? I'm not going to talk about this data, nor I'm not going to talk about elevation data, soil data, methodological data, hydrological, disease, and pest management, and so on. There are a lot of data sets that are available. I'm just saying, I'm just giving free source of data, GODAN, open data, and a lot of data coming from the European Union because they have a lot of agencies talking about data. And there's the very general initiatives to make open data more available to a larger audience. And here, of course, we are talking about farmers, or at least people working in agriculture, and there's a lot of data on that field. So since I'm going to focus on the farm-level data, I would like to focus my talk on what can we do on getting data in a more automatic manner. How can we get data by capturing automatically this data at farm level information? So I'm going to talk about, okay, we all know this kind of scenarios. Many of you are familiar to the fact that we could deploy sensing system, then we could move from the simple, let's say, sensors to more connected agriculture, where all the components of the farms could be connected, could be linked to some kind of decision-making system, databases, or whatever, in order to end up with these pictures of the connected agriculture, okay? We could have drones, we could have remote sensing, and a lot of things. The question is, how many farms can deploy such large-scale sensing infrastructures, okay? So this is one of the key research orientations that we have been doing in the last years. And we have been deploying, we start by seeing low cost, but I prefer the term cost-effective. And cost-effective means that you want to be able to design, to develop solutions that at a low cost, but still maintain a high level of accuracy and provide, of course, efficiency. And so we start developing this almost 10 years ago when we deploy sensing systems in many African countries, so-called developing countries. So we start with several European projects, was indicators, and the more we come, the more we scale in order to reach the end users. And the more you scale, at the end, you want to try to take into account as much as possible the needs and the constraint of the end users. So we have been working a lot with smallholders in these countries, and the need to automatically capture data is very critical in all countries, okay? So including in France, where we have a lot of technology, but believe me, the solutions that we develop in developing countries could also be applied in developed countries. When we talk about cost-effective, I think that cost-effective is something that you have to keep in mind everywhere in the value chain, okay? So here, what we propose in one of our projects is a cost-effective, so ground sensing system, because by sensing system, you know, we have remote sensing with satellite data, we have drones. We are here more focusing on deploying ground sensor systems. A lot of data can actually not be obtained by remote sensing. So you have to try to correlate this data obtained by satellites or drones by more accurate or more localized ground sensing systems. So what we wanted to do with by developing this kind of systems is allowing everybody, including the smallholders, including the, you know, the small exploitation farms and so on, everybody to be able to more easily get access to capture data, to be able to deploy sensing system in order to feed automatically, get automatically data from the field and feed any databases that is needed to use this data and to hopefully process and ultimately maybe share this data. So what we wanted to do is to have something like a very autonomous starter kit. So we started with soil moisture data. So we have, maybe I have a pointer here. Is it a pointer? Okay, I don't want to touch the remote control because maybe, okay. So we have soil moistures. As you can see, we have two types of soil moistures. One is a more simple capacitive moistures, soil moistures, but one is like a tensiometer soil moistures. What I want to say is, it's not the sensors that are important. It's the fact that the whole platform is more cost-effective. And you can deploy the whole system without any internet access, okay? So maybe it's not very critical in developed countries like in France. Maybe everybody has internet, but I'm not even sure that in remote areas, maybe you want to deploy sensors, but actually you don't have access to internet, or because cellular access is not that easy. So what you want to do is to be able to collect data and have like a customized gateways that is available somewhere in your field that could collect all this data and that you could synchronize later on when you have internet access, okay? So we try to develop something that is as versatile, as flexible as possible to be able to quickly and rapidly deploy sensing infrastructures. There are several things that I want to say here as the lesson learned. We design open sensing hardware. So we design very, in that project, we moved from version 1 up to version 5, as you can see, and there has been a lot of feedbacks from the users in order to be able to propose the more adapted platform, okay? So here, it's a very, let's say, cost-efficient, very robust. We could say very simple, but simplicity is not something that is not good when it works, okay? So here, we really wanted to have every part of the shelves, open source design, where you could design your own sensing platform. We validated the robust integrations. Actually, when we are running this kind of sensing platform in developing countries, we are also doing a lot of capacity buildings, a lot of training sessions. So we are, from scratch, building the whole sensing system to show that it is possible to design a robust, efficient, and accurate sensing system that can work and operational on the field. Okay, so we do have solar panel version and so on. I'm not going to spend too much time on this, but sometimes solar panel, we may think that it's good, but when we're talking about smallholders, solar panel adds lots of complexity, fragility to the device, and so on. So we prefer to be able to run on batteries. And we designed the whole system to be able to run on 2 alkaline batteries for more than 2 years. Okay? So you don't need to worry about it. If you say to somebody, okay, deploy your sensors, but you have to change the battery every 3 months, nobody's going to buy it. Okay? And when you propose something that is cost-effective, but you say, okay, it's cost-effective, but you know, you have to trade off between accuracy, and then you have to trade off between the lifetime and so on. Even if it's cost-effective, nobody is going to use it. Okay? So when you want to propose something, so we spend a lot of time optimizing all the energy management and so on. So everything is open source, everything is available. We have a lot of tutorials, but that was one thing that we really wanted to be able is to provide a full autonomy. Regarding the data, there are following talks who are going to talk about standardization, interoperability, and so on. When we talk about data, we have to be, it has to be open data. Okay, if we want to share this data, it has to be open data. So for us, it's very simple. We are not a company. We are building open source design. So all the specifications of the data are I would say, are simple and are open. And we wanted also to test, and that goes to the sharing part of data. We also wanted to test the concept of embedded AI on the gateway itself. And we proved that running on simple, this is a Raspberry gateway, okay? Of course, casing can be made more robust, but it's just a matter of casing. We have other casings that could be deployed in the wild. We can run embedded AI on the data collected from the sensors directly on the gateways. And if you want to synchronize, I mean, you can always synchronize, but if you don't have internet connection, then you can also work completely offline. And this is something that is going to be, I believe, more and more interesting, having system that can be deployed and run in full edge mode. Okay, so this is something that is very important for us to be able to provide both. Okay, if you're able to work offline, when you have internet, you will be able to do it. But if you design your whole system relying on internet servers and very heavy AI processing, inference, and training, and so on, when you don't have internet, then you can't do anything. Okay, so this was something that was also very important for us. More data allows for more correlation. So I'm here. I've been invited as part of a new project, which is from the peer-peer agroecology, so agroecology and digital, which is called AgriFuture. Officially, it starts 1st of February. So as you can see, it's the very beginning of the project. So in this project, we are more than 12 partners. So I'm one of the partners. We are more in charge on the sensing infrastructures on how to collect this data. So it's always a matter of trade-off when you want to collect data. What I want to say is, it's not because you want to propose, or it's not because I'm developing a cost-effective solution, open source solution, that I'm saying that the big companies selling high-end sensing systems, I'm not saying that they are not doing a good job. They are doing a good job. As you can see here, the efficiency of these systems can be very high. Okay? But what I'm saying is maybe the cost is not adapted for some communities. And if we want to generalize the collection, the monitoring, the sharing, and the use of data, then we have to deploy more sensors. And to be able to deploy more sensors, I think that there's a synergies between high-end sensors, if you can afford it, and then more cost-effective sensing system. So in this project, we are building a whole platform for generic sensing. So as you can see, we started with simple soil moistures, but what we want to be able to do is to connect various types of sensors for more agroecological practice. So one of our objectives, we hope that we will be able to reach it, is to better qualify and quantify the impact of these new practices. We all know that maybe we have to change the practices, but we don't know exactly what would be the impact of these practices, okay? So this is one of the goals of this project. I'm not going to talk about remote sensing, I'm not talking about satellite data and drones, but definitely I want to mention them there because, as I said, the more data you have, the more correlation you can make. So there's a lot of correlation you can make, of course, by coupling this data from remote sensing and especially satellite data to the ground sensing system. What about AI? I already talked about AI and I already talked about the data sets. And of course, we all talk about AI. We all want to have some kind of AI-based processing. But AI needs accurate data, okay? So one of the goals of this project also is to use a platform to build data sets, to build very accurate data sets, okay? Because if you have in hand a platform that you can deploy out of nowhere, that can run autonomously, that can capture what the farmers is doing, then you can build real data sets. And I'm talking here because we work a lot with African countries, so North Africa, Sub-Saharan Africa, and so on. The fact is, they are using data sets that have been built in Europe, in the US, or somewhere else in the world, because we don't have big data set for Africa, okay? So the problem here is if you are able to deploy a cost-effective sensing system very quickly, you can use it for planning, but you can use it to build data sets, okay? And this is one part that we are going to do in this project is to make use of this platform to build accurate data set. Okay, let me speed up a little bit because we are more speakers in this session. So we are also working on image sensors, and this is quite challenging. We are not working really on hyperspectral camera spectrometers, but we know that they are very, very promising. We are more working on the hardware and software platform to make image sensor possible. I'm not talking about simple image sensors where you just, let's say, have embedded processing. This kind of device exists. I'm talking about image sensors that are able to, of course, process locally data, but also transmit images. And transmit images on a long range, okay? We're talking about image transmission with several kilometers and so on. So we are using state-of-the-art LoRa transmission technology to send very small images, but we can transmit the region of interest, not the whole image, for instance, okay? So this is something that is quite promising, especially for agroecological processes, because you have to try to capture in a very indirect way what could be the impact of your practices on biodiversity, on the quality of the soil, and so on. Now, I'm going to finish my talk by talking about sharing of data. It is a very sensitive subject. As I said, even where my data is stored can be very sensitive, okay? So not even saying sharing. What can we do? Actually, do we need to share the data, or the final objective is to share the knowledge? And this is something that is a little bit different, okay? Sometimes you don't want to share the data, but you are quite willing to share the knowledge, okay? So there's a lot of techniques that we have been experimenting. We are neither AI expert, so not robot expert, not AI expert, but we know how to use some AI techniques, and we experimented it in various of our projects. So we try federated learning, and we try transfer learning. So for those who don't know these very innovative technologies, they are quite promising. Federated learning, you see on the left, is you have several farms. Each farm builds its own model because they deploy their own sensor, they build their own data sets, and they build their very accurate, let's say, model for potatoes, okay? And the farm next to you is building its own model, not for potatoes, but for maybe carrots or whatever. And then what you're going to do with federated learning is you are not sharing the data, but you are sharing the models, and at the end, you build a model, a single model, that takes the good thing of both models. Here, we have more than 5 farms. We could have 5 models. And at the end, we will have a model that could be able to handle nicely potatoes, carrots, and whatever else. Okay, so this is what we call federated learning. And the nice thing is you're not sharing your data. Your data is not going public. Okay, transfer learning is a little bit the same objectives. Is you have an already trained model, and you give the model, you don't give the data. You give the model, okay? And then somebody else could use your model and enhance your model with its own data. So nobody's sharing data, okay? So I just want to show, to say to you that we have been experimenting these 2 innovative AI for sharing data, or more exactly, sharing knowledge. And I believe they are very promising. So here I'm going to finish my talk, just to say that we have been experimenting the federated learning, we have been experimenting the transfer learning, showing that actually when you're doing that, you are able to improve the accuracy of the models. So that's all, and thank you for your attention. And there are 4 speakers that will present the other aspect of use and sharing of data. Thank you.
Thank you very much. We have time for 1 question. Or everything was super clear? Okay, so I think thank you very much. Everything was super clear. And now our next speaker is Joep Tummers from the University of Wageningen, and I will let you the floor.
Yeah, bonjour tout le monde. C'est froid, n'est-ce pas? Good morning, everybody. I'm delighted to have you all here for my talk entitled Creating Order in the Chaos, Standardization and Interoperability in Agriculture. My name is Joep Tummers. I'm a researcher on information management at the Wageningen University and Research, and today I'm presenting on behalf of the Next Gen High-Tech program, a Dutch initiative driving high-tech innovations in sectors like agriculture. In the next 10 minutes, I'll highlight the challenges and opportunities of data standardization. why does it matter, and how it shapes the future of farming. We'll have time for some questions at the end, hopefully. And if you're curious to know more about the Next Gen High-Tech program, visit their stand at the Dutch Pavilion at the exhibition. So let's dive in. Do I have a clicker here? So Wageningen University and Research is the only university in the Netherlands fully focused on agriculture and life sciences. Our research spans livestock, marine, plant, and where I'm from, social and economic sciences, with locations spread across the country. Although they look very far away, remember, we live in a tiny country. They're at most 2.5 hours apart from one each other. So now let's dive a little bit into today's topics. Drones, robots, and farm management systems make farming more efficient and sustainable. But on the other hand, they also add some complexity. Farmers used to communicate face-to-face, even across languages. Now we have machines talking to machines, and machines talking to humans, and humans talking to machines. And they all speak different, often digital languages, making seamless collaboration a challenge. For many farmers, the digital revolution can be quite overwhelming. Instead of just farming, they're now more data managers, juggling systems that don't speak the same language. Every decision, planting, irrigation, harvesting, is driven by data from drones, robots, sensors, machines, and other kind of informations. But farmers, they didn't sign up to troubleshoot data formats. They signed up to just simply farm. So how do we simplify this digital chaos we're currently in? So that's where interoperability comes in. So imagine a machine with rusty, mismatched gears. Instead of running smoothly, it grinds and slows down. This is what happens when farm technologies can't communicate properly together. And this is what we call the interoperability problem. Systems don't speak the same language, making it difficult to share data, and farmers lose control over their data as big tech and machine manufacturers lock data away. But luckily, some change is coming, especially here in Europe, with the EU Data Act, the Data Interoperability Act, pushing for more transparency on data ownership, easier data sharing between systems, and less vendor lock-in for farmers. But this isn't just a European issue. It's a global challenge. So today I want to bring you on a journey where we zoom in from the global perspective to the European perspective, and at the end to the Dutch perspective. So let's start with a global perspective. Agriculture is more connected than ever. Data doesn't flow as smoothly as it should go. Think about a Dutch farmer might export crops to Asia, relying on data-driven logistics. A German tractor should work with US software and Japanese sensors, but often it's not going as smoothly as we wish. It's not play out of the box. Sometimes regulations differ over different countries. Europe is very much pushing for open data sharing, but not every country follows the same rules. Right now, poor data interoperability means inefficiencies, extra costs, and lost opportunities. But solutions are luckily emerging worldwide. Just want to zoom in a little bit on a committee we are involved in at Wageningen University and Research. There's the ISO, International Standardization Organization Committee, TC 347 on data-driven agri-food, and they ensure farm technologies can speak the same language. Think a bit like ISOBUS did for tractor and implement communication. This is more for farm management systems to properly communicate with one another. So what does it cover? It covers things like crop data, agriculture semantics, livestock data, but also more robots, test maps, that kind of information. So it's being led by the German and the US Standardization Organization, and they have partner organizations from all over the world, and we are involved in the Dutch Partner Standardization Organization. Currently, it's still quite abstract. They are now in the phase where they are thinking about where are we going to develop standards for, on which topics do we need standards, and it's expected to be more concrete over the coming years. Next, we zoom in to a very old map of Europe. Although this looks very old-fashioned, Europe is actually quite much on the forefront of modern data interoperability in agriculture. From EU regulations like the Data Act, Data Interoperability Act, cutting-edge data spaces and standardization efforts, we are building a connected, farmer-friendly digital ecosystem in Europe. So let's talk a little bit about data spaces. Sounds very complex, Can be very complex, but that's currently what we are working on a European level in several projects. So what is a data space? A data space is basically a secure, decentralized system, just like the federated system that was presented by the previous speaker, for data sharing. So it's not about sharing and storing data in a centralized database. It's a federated system where data stays at the source, but there's a generalized way of accessing the data. So data stays at the source. Interoperability is used, so different platforms can connect seamlessly. There's trust and governance, so there are clear rules and regulations on what cannot be done. And for example, data spaces are already being developed and are quite far in, for example, the health sector, mobility sector, and financial sector. And within Europe, we are now starting with the data spaces. So a previous project where we were involved in was the Agri-Data Space project, where we helped predefine all the key conditions for data spaces. So more about governance, architectures, business models. And the next step will be in an upcoming project, the real implementation of a data space. Now we zoom in quite deeply to a very small country, the Netherlands, where we do not only make cheese and produce windmills and that kind of stuff, but we also work on the implementation of our own data space in the next-gen high-tech project called the Hollandse Datalinie, which doesn't really translate very nicely to English, into Dutch data line. But it's a project where we can say we built a Dutch implementation of a data space. So how does this work? This is like a federated system again. Farmers decide who access their data. I will go into the technicalities a bit later. And you can see it like a Google Drive or OneDrive system for farmers. Where they access their data, manage their data, and each farmer has their secure own data space. It's built on top of a connector library that can link all kinds of data from farm management information systems and other applications. And therefore, a farmer, instead of juggling multiple systems, farmers get one unified, easy to manage digital ecosystem. One of the most important things here is governance. So trust and clear rules on data ownership are just as important as the technical standards to make this work. To have this, we need, and they're also in our project, the farmer organizations to protect the farmer interests. We need farm management information system developers to ensure seamless integration with the already existing systems and what's already out there. We need supply chain partners and policymakers to align on data sharing agreements. And because without a strong governance around this kind of technology, we risk creating a very nice technology, high technology driven solution that looks great on paper, but just fails in practice. And at the end, we want happy farmers. But right now, they are very much confused, overwhelmed by complex digital systems. And with implementing this Dutch farm data space, we try to make life a little bit easier for them with less hassle, more control, and a stronger digital foundation for the farmers, and means a strong future for the farmers. A little bit about the architecture around it. I don't want to dive too deep into this, but to really put farmers in control, we need a secure, flexible, decentralized, federated system, and this is where we use SOLID for. SOLID is a federated data system. It's created by Tim Berners-Lee, also the creator of the World Wide Web that we all use on a daily basis. And it's already being used for application healthcare and finance, and now we're bringing it to agriculture. So how does it work? Each farmer gets their own personalized pod, a secure space for their data. They choose their pod provider, so there will be multiple providers of these farm data spaces, like selecting, am I using Google Drive, OneDrive, Apple iCloud. Pods are portable. Farmers can switch providers while keeping control of their data, and the data stays decentralized, so it's not locked into a single platform. So key benefits: full data ownership for the farmer, farmer controls access, no vendor lock-in, data can move freely between the pods, and there's better security and privacy, so there's no reliance on big tech here. One very important thing here is the semantics. So how do we make sure everything speaks the same language? That's also my topic of research. So at Wageningen Social and Economic Research, we provide the semantics for this farm data space. So different farm systems use different terms for the same thing. One says field, the other says crop field, etc. causing confusion and blocking smooth data exchange. Therefore, we have the reference model Agro, RM Agro. It's already a reference model being used for agriculture since the 1980s, so it's already out there quite a long time. And we're currently modernizing it into a new form in the form of an ontology, which is a machine-readable way of specifying data formats and definitions for data. We align this with other initiatives like SARA for Agri and the Agriculture Information Model, and this just helps the data and computers can understand one each other. Now, zooming out again. In conclusion, we've made huge steps in building data interoperability over the years, from global standards like the ISO to European data spaces to more farmer-controlled architectures like the Dutch farm data space I've presented last. They also go from quite global, vague perspective into more hands-on applications on a national level. But let's be clear, we are not there yet. And in fact, this work will truly never be finished. Technology keeps evolving, regulations change, and new challenges will arise. Interoperability is not a one-time fix, but it's an ongoing effort, a continuous process of improvement, collaboration, and adaptation. With continued collaboration between researchers, industry, policymakers, and also farmers, we can make data work for agriculture for now and in the future. I thank you very much.
Thank you very much for your talk. So we have once again time for one question from the audience. Yeah. No question? Okay, since it's 29, we're right on time. Thank you very much for your talk.
Yeah, thank you.
Thank you. Okay, and now please welcome the next speaker, who is Alexis from INRAE, who will talk about energy consumption.
Hello everyone, I'm Alexis, and here today I will talk about our research titled Toward a Better Understanding of Robot Energy Consumption in Agroecological Application. It was conducted by the TSCF team in the INRAE Institute. So first of all, I will introduce the subject, show the contribution of our research and the literature review, and then I will explain the actual research itself with methodology results and a short conclusion. So as you know, agriculture now has to face new challenges as the population is growing and the climate crisis does a lot of damage. So robotics can be part of the solutions that could bring new possibilities to agroecological practices. Just as a reminder, agroecology is incorporating ecology principles into the agricultural practices. So as part of it, it's a reduction of the resource use, so also the energy that can be used. And robotics can bring new possibilities that didn't exist before, as like monitoring the energy consumption in the agricultural processes. But for now, there is a real lack of energy-focused algorithm in the research and in the agriculture. So that's why we conducted this empirical study. The contribution of this study is, first of all, to analyze the data set of the energy consumption of an agricultural robot through different parameters as speed level, battery charge and temperature, rain accumulation, but also the implements we used. And like this, we provide a short analysis with some recommendation on how to optimize the energy consumption for agroecological robotics. First of all, if we talk about the research domain, we can find 3 different topics about energy and agriculture first. If we look at it, we can see that agriculture is really high consuming in energy and mostly rely on fossil fuels. So that can be one of the solutions of robotics, is to change these practices. So if we look about robotics and energy, we can see that there is 2 types of optimizations, like first of all, hardware optimization, so the component of the robots, and software optimization, the algorithm itself, and we can also combine both. And finally, if we look about agricultural robots, we can see that in that case of real-world application in agriculture, the locomotion aspect is the most driver of the energy consumption. So it will rely more on frictions parameters and so on, and not on the computation process. So that's why on our study we really analyze the parameters of the locomotion itself. Finally, if we conclude on the research topic, we can see that there is few parameters that impact the consumption. The higher impact parameters could be speed, the task performed, the ground slope, the weight load, and the braking frequency, and then followed by the center of mass location, the type of ground, sandy, and finally a lower impact on the turning radius and the terrain type. But compiling all of that, we can see that there is really a lack of real-world focused analysis. So that's why we conducted that empirical study on our robot of POM Sabiagri, which is 1,200 kilograms and equipped with laser obstacle detection, LIDAR, which was not used during the experiment, but for other experiments. Also equipped with GNSS guidance, which was used during the experiments for doing the trajectories. An optional manual piloting for driving the robot if needed, but it is totally autonomous. And finally, maybe the most important, it is designed to perform different agricultural tasks. So you can attach different tools on the back of the robot and perform different tasks on the field. The tools we used are the 4 you can see here. First, the seeder, which is maybe one of the lighter to implement we used. The cross-kill roller and the vibro cultivator, who are more heavy and for soil preparation, deep soil preparation. As you can see on the video, it's the vibro cultivator. And finally, the harrow, which is light also and more for narrow soil preparation. So we analyzed the different tasks the robot performed, and we tried on different type of terrain, as on field, on grass, or on asphalt, as the robot also go back to the garage and so on. So it really provides a large-scale analysis. And finally, the data we could compile was composed of 69 trajectories that were recorded, and 22 kilometers of accumulated distance traveled, and a lot of parameters that we collected and assessed, as the power, the speed, the position of the robot, different type of implement, the weather condition, battery state, and the terrain type. So as you can see on the figure, there is example of 2 different trajectories. The first one you can see on the left is the robot performing an agricultural task on the field. you can see that it's really energy consuming, going up to 10 kilowatts consuming. And another type of trajectory, which is simply going back to the garage. As you can see, it's less consuming, and it really shows the difference of trajectories we could analyze across these 69 trajectories. So a large and varied data sets that we could use. So finally, the analysis showed different results, but now I will just focus on one parameter that we will assess is the speed level of the robot. So we choose to show the data as violin plots. So you can see on the left axis the power consumed at each time, and on the bottom axis a different range of speed level. The violin plot is composed of a box plot, which shows the interquartile distribution between in the black box, and also a distribution plot showed by the line of the violin. And finally, a data count just below the violin, which shows how many values we used for assessing. So as you can see with that graph, we can clearly see a correlation between the velocity and the energy consumption of our robot. But as you can see, there is some variation on that graph. So it was really interesting to also make a differentiation with the tool, with the implement we used. So it leads to different graphs and also characterization of the energy consumed by each tool. So it's typically the same graphics with the velocity which is assessed, but classified by the different tools I showed before. So as you can see, the heavier tools as the vibro cultivator and the cross-kill roller are the more energy consuming, and the seeder and the harrow are less energy consuming, but we can see a sharing tendency between all the implements of increasing the velocity will obviously increase the power consumed. But as you can see on the vibro cultivator, it also shows different tendencies as a flat part from 1 to 2.5 meter per second. So this can really lead to decision making for what is the better speed for performing a task. It's really possible to create optimization in the algorithm depending on the tool used and the optimization between time consumption and energy consumption. So finally, to summarize, I would like to conclude on the main focus of this research is that the main parameters that will affect the consumption of the agricultural robot, the energy consumption of the agricultural robot will be the speed and the task performed shown by the tool equipped with a classification that is hard to see on the left, but I will detail. So first, the most consumer is cross-kill roller, then the vibro cultivator and the seeder and the harrow, and finally, with no tool equipped, it's the less consuming. Finally, this short study will show clearly that there is a possibility of analyzing the energy consumption of your robot, and that is not really hard to implement, and that really shows the opportunity and the difference that you can implement for your type of robot, which is very important to implement in the agroecological practices. That's why for the future researches, there is a big necessity of conducting that type of energy-driven analysis. To remind you that robotics will be a big part of the agroecological practices, but they have to face that current challenges of energy saving and energy consumption. Thank you. Here you can find a link to our research paper, and you can also contact me by mail if you have any question. Thank you.
Thank you very much for this talk. We have a bit of time for questions. So, has anyone have a question? Yes.
So thank you for the interesting presentation. I was wondering, why did you decide to express the energy consumption in kilowatt hours and not in something like kilowatt hours per hectare or area of cultivated land?
It's a nice question. We wanted also to assess the parameters over distance to see the actual effect of the energy consumption for a whole task along the field, for example. But for that study, we only focused on the real-time energy consumption to characterize the robot for future algorithm-driven for energy consumption. But that's a future research that we will conduct on that topic, which can be really interesting. Thank you.
All right, then we have time for one last question, if there is one. Oh no, so everything was very clear. Thank you very much.
Thank you.
Okay, then for our third talk, please welcome Catia Pinto for the Smart Farm Collaborative Laboratory.
So, good morning to everyone. Thank you so much. And again, it's a very pleasure to be here in the World FIRA. So it's really nice also to share some of our work. So as a previous colleague, I also to invite you for a journey not so far away from the worldwide. Let's go to Portugal. So I would like also to invite you to come to our little also association. So we are not a company. So we are in the middle between the academia and also the companies. So let's say we are a little bit of the facilitators of the brokerage of the new technologies that in actually the production needs. So one thing that I'm going to talk about today is about intelligent spray management. That is a work that we are doing also with our members, and actually the need that we have to have the robust data and set collection to treat them, and also that makes sense to what we need in the agriculture. So okay, so who we are? So we are a Portuguese reference for digital innovation in agriculture. So our name is the Smart Farm Colab. That means that we are in the transfer of the knowledge and also the scientific knowledge between and technological from the academia into the companies. And we are in the middle working with them. So our focus is on the digitalization of the agriculture. We develop services in this way, and that's the reason why we call us like an helix quadruple entity, because we have all together like members of academia, SMEs, also the public, because we create also public awareness. And one thing that is really important is the society, because everything makes sense when we put also society and we work this knowledge all together. So we innovate. What we do actually is also to co-create innovation. That's the reason why we have these all kind of members together, but in the way that these solutions make sense for, for farmers. So if I can describe what we do, like in the Smart Farm Colab, we are promoting the adoption of digital technologies. And so when we design these solutions, we need to take in account the cost of the solution, so the investment, and how can we return also these investments in terms of the use of them. And another thing is that, okay, we can have these solutions, but if we don't have also the training, the specific training to use them, maybe we'll will not be positive. So we work on these actions together. So one side is democratization of the technology in terms of the agriculture 4.0, but also performing this training and is helping to farmers. So we have different members, as I said before, academia, SMEs, some of them, maybe you know them, because they have a lot of works worldwide. And something that we need also to create is this kind of awareness. So when we are developing these digital technologies, I would say that we have 4 main stages, maybe more, but these are the more, the more use and the stages that we have working on. So we have the systems that is in the field, so collecting data. We need to treat this data, so the data transmission that is really needed, and we know that the connection is the communication is something that misses in rural areas. Still, we have a huge work on that. We have this kind of data processing, the data analysis, knowledge bases, but the important is to create this information in useful information. And to create that is something that sometimes we forget, and this is, I guess, the success of different technologies. That is the integration with the farmer, so the end user. We need to integrate these technologies where we are developing them with the farmer that is the end user, otherwise they will be disconnected with reality. And so this is not only develop the technology, but also perform this digital literacy with them and so on. We can have the interaction and maybe perform things that are really useful and that we need right here and right now. And so just to point a kind of awareness, and this is something that in Smart Farm Colab we saw during the years, is that we have, and this is something that in practices, we have a lot of entities and good work on that in data acquisition. So we have a lot of effort on that. Actually, a data of analysis, we started to have differences here. So we have a lot of data acquisition, quite poorly sometimes developed this kind of data analysis. When we have these personalized, technologies and also solutions for decision making, here starting the problems, starting it, because we can have this quite poor performance, and the worst case scenario is sometimes the integration with the farmer, that a lot of the companies and also institutions omit this part. And this is one of the most important for that, if we want to get this solution really adapted for the needs in the farming processes. So this is a project, and we have also a stand here, so come also visit us. We don't have this robot, it stayed here last year, but just to point it out some of the works that we have been developing here. So this is a project, it's a national project in Portugal that we call the Tech for Green. There's a lot of partners involved of them. And this part is the work package that we are responsible for it. So we have different entities, two companies, so Tummers and also Uninova, has a Smart Farm Colab, so this operationalization center, and also the Uninova that is the academia partner. So what we are developing it is like a kind of working with intelligent spray management, but actually we have these real-time production factors prescription that we are working on. So we have different objectives that we have. I would say I will present you in the next time. So the pilot with the purpose that we have, and we're starting up of these technologies that we call is SOFIS. That is different sensors that we are developing it, adapted. This is not new, it's adapted from what exists in the market in the low-cost profile and also in the literacy to promote this adoption of the technologies. So what this office do is like a modular system in way we are controlling or measuring the information in the proximal sensing. So this is proximal sensing sensors. Then we have this all information that we know, so the clouding, the processing analysis, and then the decision making. So what we have in this field, So this is what we decided, what kind of information that we need to perform, and actually to communicate with the spraying, and so we can perform is spraying management in an intelligent way. So for this, in this pilot, so it's also in Portugal, we are working with pears and apples. So we have different sensors in the field. So we have the meteosurface, that is the meteorological station, so everything is low cost. We have the soil sensors, we have the eye trap, so this is a low-cost eye trap also for different pests. Then we have the vision, so the computer vision analysis performing. So this is the model of the orchard that we have already, developing also with the Uninova, so the 3D model of digital models of the orchard, in order so we can have all these pictures, so putting a lot of information in something that can be useful in when we are promoting the spraying. And another one is the drones analysis. So try to understand not only the development of the plant according to the campaign, but also to understand the volume of the plant, so the canopy volume, and also the height of the plant. And actually, what we want to do is all this information that we have, we are integrated into a management system. But not only, so we put here the analysis, for example, of the sensing, the remote sensing, another platform, no. So we put everything together. So this is the huge work that we are having, because we have so many data that sometimes the problem is, and now what? And so this is putting the interesting point, so what kind of information that we can put it out from here to put it into the spraying. So what we need spraying information, so the machine for the equipment, so they can perform its actions. So this is all the integration. So now what we are doing is developing also a model. For example, this is drone images that we process. We put them into the platform, and then here in this, in the other part, sorry for that, in the other part, so we understand already the plant per plant, the status of this plant. So in terms of the volume of the plant, the vegetation, the diseases, probably this is the second point that we are integrating them. So in order that when the equipment, so in this case the spraying can pass, he knows exactly which kind of the plant he needs to spray or not, and the quantity. So this is the example of the spraying. So we are starting from our starting point, what was a robot for the greenhouses, and now we are working the orchard, so the apples and also the pears. Not with the robot still, we still have a lot of work to do, but also one of the points is to develop different kind of the machines that can be integrated, not only from the greenhouses, but the particular one from the orchards, and also for the tomato production that is completely different when we have in the fields. So this part is with the Tomics. So they are integrated now. We are doing some tests with different equipments, and again, the more challenging one is to putting all the information that we get. So this was the first campaign, but still we have the historical data from this previous pilot. We are now in the second campaign, and I hope if we come next year too, to bring you some pictures and maybe the robot here, what we did in this campaign of 2025. So just to have an idea, so this is the future, but the past is also important. I put it here a video because this was the starting point of our robot. This was on the Smart Farm 0.0. It was a robot that we worked is a modular robot from the greenhouses. So we have different cameras that recognizes what is going on. So the vision, the computational vision images is collecting the data, integrating, and then we have two phases. So one is the robot that picks the fruits. So it recognizes the size and also the color. In this case, it was the tomato, but can be, for example, for other kind of vegetables. And actually taking analysis of what's going on to predict the next campaign, and also to pick correctly the fruits. So this is the part of the robot in the front, but then we can also changing for another one as we can going to see. So he's finished his mission, he's going to home. And the second one, so we still have this modular robot in the front, but then in the back, we can have it, and this is our point for this project, is working with this spraying, so it's intelligent spraying. This is electrostatic spraying for the greenhouses, and what we are going now is adapting them for the orchards. As I said, it's a small robot. The orchards is completely different, so will not be for sure in the next step will not pass exactly. Probably for the robot, we will need to improve them. And so this is just to show the precision spraying that we are developing, and this kind of electrostatic developing spraying. So, okay. All the work, and this is something is important to show because there's a lot of people behind of everything we do. This is our team. It's not a sensation-wide team. It's like a team that wants to work for the future. We have different partners also involved that I'm not showing here, but we are also very happy if we come to see our stand. We are over there and to discuss a little bit of our work and maybe future projects, like say. Thank you so much.
Thank you very much for this talk. We have time for a few questions from the audience.
Any questions? Don't be shy.
Okay, so no questions from the audience?
Maybe no questions.
Okay, so maybe one from me then.
Okay.
You talked a bit about gathering lots of data, but have you for now have any strategy on what data to gather? Because if you gather everything, it will be a ton of data. So do you have
so
any
I
way
didn't
to...
understand.
Sorry.
We have a lot of data?
Yes, and do you have any strategy to select which data you want to keep and you want to use afterwards?
I didn't
Yes, sorry. Yeah, so you have lots of data. How do you select which one you want to use afterwards?
So this is the use of the problem, right? Yeah. Because sometimes the thing is that sometimes we don't know what the thing. I mean, we have always to know what is the problem. Well, in this case, for us, the challenge is what the machine needs to learn from us in order to get a good mission. This is something that we are learning, so we don't have still the solution. So we are taking maybe more data than is needed because we still don't have, for example, how we can program everything in the machine. Because we need, in this case, what we need is, for example, to have a good picture of all the orchard that we are working. And so that's the reason why maybe the high trap sensing that we are using for the pests, maybe we'll not need it because it's just spraying, in this case, it's for just spraying for the diseases, not for the pests. But we are taking also this information because maybe in the future we can use it. So for now, maybe a lot of data that we have is only storage as information. Because one thing that is really important is that in agriculture, quite different from the banks, for example, that have a lot of financial information that can use all the time. In agriculture, no. For example, if we had 3 years of data, non-interrupted data, it's not enough. So we need a lot of years to have this data in agriculture, and sometimes it's really hard to have it. So I can tell you that the data that we have already is not enough to do, for example, models. So we need maybe 10, 20, 30 years, 40 years, which is really difficult in agriculture.
Thank you very much.
You're welcome.
Thank you for your speech. I have a question. You just mentioned that the data is important, or data are important, but the mission is also important. How could we identify the optimized mission? Because that's also one open question in my mind, honestly.
No, yeah, actually, it's that's the reason why, for example, in our case, we do exist because to match the needed and also what we can do. For example, if I can tell you, in our institution, so in Smart Farm Colab, the majority of the team are agronomic ones. And so they know exactly the needs of the field. And so it's kind of a translation that we perform into the technical part. Because we need to communicate, and the communication is not only the communication that we have from the machines and the clouds, it's also the human communication that's really important. I would say that in terms of the mission, first of all, is us. We perform this mission in the way that we understand the problem and the needed. And then we try to work with another mission that is to learn with the machine, or try to have insights with the machines and to perform the different missions in the field. So I think that we have different two kind of challenges, if I would say. But this is my view.
Okay, thank you very much.
Thank you so much.
Okay, now for the last speaker of the session, please welcome Eva-Marie Dilschneider from the Technische University of Braunschweig.
Not really, but okay. Okay, so welcome to the last speaker of the session. My name is Eva-Marie Dilschneider. I'm from the Julius Kühn Institute in Germany. I will talk about spot farming. So not really starting with robotics, starting with a little more agricultural theme, and then coming to the robotic theme. Yes, starting with a short introduction, everyone should know here, it's not that new. So we have the problem that the arable land per capita is decreasing and farmers feed more people, and also there are fewer farmers and the few farmers have increasing size. So what we're thinking about in the Institute, that new approaches are needed for better or smarter farming. And new approaches are possible even if there's especially while there's a development in technology. We have more possibilities to do farming, but many approaches do not call the current farming into question. So we think about what if we rethink how we farm, and then there are possible opportunities for sustainable intensification. I'm sorry. And many of these opportunities can be overlooked when we don't call the current farming into question. So we developed at our institute the so-called spot farming approach. Here we focus on the needs of the individual plant. And then we're planning to do a small-scale farming. So we define homogeneous sub-areas into our fields and want to farm them with an adapted crop rotation, and that's hopefully more sustainable, and we can also be more biodiversity, especially if we plan to adapt boundary structures like hedges to plant. Possible advantages of this over the commercial agriculture is that we have the optimal growing conditions per plant. So if we have a homogeneous spot and adapt a crop rotation to this spot, we can say here we have a spot like with these conditions and we need especially a crop rotation for this place. And when we have this, we have to apply less fertilizers or less pesticides. But then we have also a higher yield security, and if you don't have to spray that much, we need to drive less over the field, and we have less soil compaction. And we can also enhance the bio and the landscape diversity. Telling something about data, so the question is, of course, how can we generate these spots or these homogeneous sub-areas? So we need different kind of soil geodata, and actually we're working with the soil type, the soil texture, the digital elevation model, and information about the actual landscapes. I don't know how it is in France. In Germany, we have a problem about getting these data. So they're often not free, so we have to pay much more money. And if we think, well, a farmer wants to work with this data, it's a very hard problem in Germany, especially. But actually, we are getting this data during the project and processing these. So we started with manually working with these data, but actually we are on the work to do an automatic processing these different data to generate such a map. And also we need a suitable technology, and then it comes to robotic solutions. We want to think about how can we farm these smaller, perhaps smaller areas. There are robotics, a big theme. So but we also have to think about roads to this area. So perhaps we have losses due to the roads during the spots. But we also need to focus on the spots which are very good for harvesting or for crop growing. Then we also have to think about the scale of the robots. In the third thinking, perhaps small robots are the better versions because we have less losses in the roads. But we also need perhaps big robots because they are more suitable for carrying harvesters, something like that. But we definitely have to think about new process designs and process steps for the agriculture when we're doing it that way. And to make it short, I came to my conclusion. So digital data makes it available, or the availability about data makes it possible to think about new field structures or new kind of farmings. Hereby, the suitable intensification is the goal. So with the same or less input to get more output. But it's only feasible with automatic machinery because when we want to focus on a single plant, it's not a human thing we can do. We have to need some machinery like robots. Okay, so thank you for your attention, and our contact data and also a QR code for further information.
Thank you very much. And so we have time for questions. Yeah.
Thank you for your presentation. You say you struggle with data collection for landscape, but there is a database, a European database, which is called Corin Land Cover. Did you check that? Because it's highlight the land occupation. But I don't know the scale, so if you want the scale at the field or at the territory, it may be different. So there is some possible data on that.
Yeah, there are possible data, but we need a small scale so that we can work with it. But the small scale is often the problem.
So thank you for your presentation. You said that you have some difficulties to collecting the data, but I want to know in terms of the applying your strategy or methodology to the new field, how the farmers, I can say, are they appealing or are they interested in using your method in their farm? Because I think that could be like a huge change in their field, in their. It's not clear?
I didn't understand it really well.
Okay, so I don't know at what stage is your product is, but imagine that now you want to apply it in some field. Are the farmers interested in applying this, or what?
So and so. So there are farmers which are interested in, but actually we are more in the development, so we are looking for interested farmers to test it on the field. But there are also sometimes farmers which say, well, pretty nice idea, and some are, no, that's shitty.
Any other question? Okay, so I guess thank you very much for your talk. Let's have a last round of applause for every speakers of this session.